Bam! Mr. Tarrou. In this video, we're going to be taking a look at this equation. F of x is equal to 3x minus x squared. It's a parabola opening down. It's a polynomial with a leading coefficient which is negative. So we have that reflection over the x-axis. And we're going to, with this parabola, do something really, really cool that you've never been able to do before in your studies of algebra and geometry and such. We are going to find the slope of a curve at any point that we desire. See, up until now, you have only been able to find the slope of a constant line. Well, when you're looking at curves, yeah, the slope of a parabola, through some of the interval along the x-axis, this parabola is increasing. We have a vertex where the rate of change for just a split second is equal to 0, and then that parabola starts to decline. And what I'm trying to do here, I don't want to mess up my drawing, but that slope is constantly changing, and we're going to estimate the slope of a curve at a point using, well, basically the slope of a line, and specifically a tangent line. So we're just getting started into our journey of calculus, and there's all kinds of things to learn. And this study of calculus will be the first time that we're bringing motion into your studies of algebra. So we can speak of things like velocity and acceleration of a particle, not just its position. But we have to start somewhere, and that is the basics. We're going to be finding the slope at a point, basically two, you could argue maybe three ways in this video. We're first going to be introduced to the definition of a derivative. We're going to identify how closely this is related to just the simple equation of slope that you learned way back in Algebra 1. And we're going to go through a limit process to find a derivative function and then use that derivative to find the slope at 0. And that's a little bit not exactly what our directions are asking for here, because it just says find the slope. It doesn't say find the derivative function for this parabola. But I want to do that, find that derivative first and then find the slope at 0 for two reasons. One, if I need the slope at multiple points, I can use the derivative function to find those slopes, and I want to have the derivative function and map it over the graph of the parabola we have here so that we can see how it is the derivative is related to the function from which it was derived, which is that it tells us what the slope is. And I have also a little bit of review, as I just mark it up, of putting this parabola, which is in general form, into vertex form or standard form, depending on what the book is you're learning from, through the completing the square process so that we have it in a form where we can identify the vertex and the direction to which it is opening. If you need a review of that, I'll have a video in the description, or a link in the description below. So let's get into this. The derivative, that's what this little apostrophe mark is, the derivative of f of x is equal to the limit as delta x. Now, if you haven't seen this notation before, delta just means a change. And so we're talking about moving along the x-axis and seeing how the rate of change of y is related to that movement along the x-axis. So we're going to let that movement along the x-axis, remember, limit notation, this arrow means approach. It's not going to be 0. We can't divide by 0, but if delta x, the horizontal distance that we move along the x-axis between, 2 points on a curve, that is going to get really, 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 really small and approach 0. That's why we had that chapter 1 analyzing and studying and being introduced to the idea of limits. We're not really dividing by 0. We're just really, really close to it. The limit as delta x approaches 0, two-sided limit, is equal to f of x plus delta x minus f of x over delta x. Now, this definition of a derivative given to you here in simplified form kind of hides the fact that really this is nothing more than y sub 2 minus y sub 1 over, well, let's unhide the mystery here, over x sub 2 minus x sub 1. And when you go back to your skills that you learned in Algebra 1, y2 minus y1 over x sub 2 minus x sub 1, and you see in the denominator that we have an x minus x, well, that's just going to cancel out. So a definition of derivative is just the equation for slope with the idea of a limit attached to it. We're going to let a point move towards another fixed point, and as that one point gets closer and closer and closer, our estimation of the slope is going to get better and better and better. So let's go through this process. So we're going to find f prime of x, that is also identified as with a prime symbol, is equal to the limit as delta x approaches 0. Now let's go find that function, and everywhere there is that opening variable, that independent variable, we're going to take that out and replace it with x plus delta x. We're going to take out a single variable of x and replace it with an expression of x plus delta x. So f of x, or kind of sloppily labeled y over there, is 3 times something minus something squared, and that something we're putting in is x plus delta x. And then minus, and now what I'm going to do here is I'm going to put in a set of parentheses because the function that we're working with, the function for which we're going to find its derivative, has got a couple of terms, and I want to make sure I apply that negative to each of those terms. All over delta x. Now that we have written this two-sided limit statement, can we just let delta x approach 0? Well, if I do a substitution and everywhere there's a delta x, I plug in a 0, what's going to happen is this is going to be in the form of 0 over 0, which is a form of indeterminate. We talked about that in chapter 1. That means that there may be a limit, there may be not a real limit, answer if you will, to this expression, but we don't know what it is yet. So we're going to clean up the numerator, and we hope that what's going to happen is somehow we're going to be able to allow this delta x in the denominator to cancel, allowing us to have an expression that will, well, allow us to plug in a value of 0. Make sure you write that limit statement each time. The limit as delta x approaches 0. We're going to distribute the 3 and have 3x plus 3 delta x. We're going to square this binomial, and x plus delta x times x plus delta x is going to give us 3 terms and not 2. Make sure you leave the negative in front of the parentheses. We're going to have x squared plus 2x delta x plus delta x squared. We're going to distribute this negative through the parentheses here and have, after closing that, negative 3x plus x squared. And then that delta x in the denominator. Distributing this negative through our parentheses still that we have left. Limit as delta x approaches 0 of 3x plus 3 delta x minus x squared minus 2x delta x minus delta x squared minus 3x plus x squared all over delta x. Now, with the way the definition of a derivative is set up and this process that you're going through, yes, something is going to happen to allow you to cancel out the delta x in the denominator. Basically, if any terms are left in your numerator that do not involve delta x, if they don't all cancel out, you've made a small mistake somewhere in your algebra. So let's see how we did. We have 3x minus 3x. We have negative x squared and a positive x squared, so that's really good. And we're about to run out of room here, but we have the limit as delta x approaches 0. And because I'm out of room, even though I feel a little bad here because we're kind of just being introduced to this process, but I want to kind of clean up my numerator that's going to allow me to show the cancellation of delta x right now. We don't have any like terms, so that's not really too complicated. We have a 3 delta x, a 2x delta x, and a delta x squared. So each of these 3 terms, I ignored the negatives there, are going to allow us to factor out a delta x. So 3 delta x divided by delta x is equal to 3. Negative 2x delta x divided by delta x, or factoring that out, is going to leave us with a negative 2x. And our third term here has basically 2 delta x's because it's squared, leaving us with 1 negative delta x left over. Now we can see that you cannot cancel terms, but of course you can cancel factors, and the delta x divided by delta x, that is a multiplication of delta x on the numerator, so that is going to be able to be canceled out. And we have, I'm going to go sideways, which is leaves the door open for getting linking errors in your work if you're not super careful with what you're writing, so not generally a really great idea. 3 minus 2x minus delta x. And now if I go ahead at this point, I finally have an expression that it's going to allow us to let delta x approach 0, or kind of just allow us to plug in 0, and we have 3 minus 2x. What does that mean? Well, let's come over here and let me fix my remote control down. Fix my notation over here that I didn't like. We have f of x is equal to 3x minus x squared, and now through this definition of a derivative process, what we have, and I'll do it in yellow, is f prime of x is equal to 3 minus 2x. Now, watch this. I have the graph of our parabola opening down. On top of that graph, I'm going to now graph y is equal to 3 minus 2x. We have a line whose y-intercept is 3, so we're going to go up to 3. And the slope is negative 2 over 1, so we're going to come down 2 over 1. We're going to go down 2 over 1. And down 2 over 1, and if I happen to manage to draw this straight enough, hopefully we're going to see a nice relationship between a function and its derivative. And this is something that we're going to be doing a lot of in our calculus class. It's really important that we can look at a graph and just sketch its derivative function even without going through this process of algebraically finding its derivative. We have, it's always hard to kind of get this to a point where kids understand it, so we're going to see if we can't point to what's going on to help out. We have here a parabola that's increasing on the interval along the x-axis, along the interval of negative infinity to 1/2, and then we have, that would be 1.5, and then we have a parabola that is decreasing along the interval on the x-axis from 1.5 to infinity. So an increasing function means that it has a positive slope. And at this x value of negative 1, where the function is increasing, we have the derivative. The answer that we get from a derivative is slope. So here at negative 1, maybe we have, I'm just trying to use this to identify here that we're getting an answer. If you plug negative 1 into the equation of the parabola, we get a y value of what looks like negative 4 if my graph is correct. But the answer that we're getting from the equation f prime of x is equal to 3 minus 2x, that answer that we're getting, which if drawn correctly appears to be an answer of 5, means the slope of the parabola at the x value of negative 1 is equal to 5. And here where we can kind of clearly see the parabola stops increase and it kind of comes up to its top, its vertex, and then starts to fall. Well, the slope goes from being positive to being negative there. So at 1.5, it seems like the parabola is not increasing or decreasing, thus having for a very short period of time, specifically when x is 1.5, a slope of 0, and indeed our derivative is crossing the x-axis at 1.5, indicating an answer, a y value of 0. So when you plug some number into a function and its derivative, if you plug that number into the original function, well, that's just a location of where it is on the plane, the vertical position. But if you plug that same value of x into the derivative, you're getting its slope. So what is the slope of this parabola at the point 0, 0? Well, now it's pretty simple. We have our derivative, which is f prime of x, is equal to 3 minus 2x, and f prime of 0 is equal to 3 minus 2 times 0, which is equal to 3. So we're also going to, I didn't mention this in the description, but we're also going to go ahead and just talk about visualizing that tangent line. So we have the original directions, which I erased, said find the slope of the tangent line to the original function. F of x is 3x minus x squared. Let's make sure you understand what a tangent line is. A tangent line is a line that touches a curve at only one point. You probably first learned how to learn about those when you were talking about circles and tangent and chords. What do you need to write the equation of a line? Now we're going to step past the directions and find the equation of a tangent line. You need a point and a slope. See, we're still talking about all this Algebra 1, even though we're getting introduced to advanced calculus. That's pretty cool. Let's get this out of the way. That's fine. It'll be hopefully not too confusing because I have the derivative graph, which is a derivative is a function that tells us the slope of another function at any given point. And you see here the parabola going through 0, 0, the derivative giving us that y value of 3, which we just found, right? Well, what is the equation of the tangent line passing through? This is a new camera, so I'm hoping it's picking up all these colors pretty decently. What's the equation of that green tangent line to the parabola? It's actually this green tangent line that is giving us the slope, if you could argue, the slope of the parabola at 0, 0. So let's figure out what that equation. You're still going to be pulling this point slope form of a line that you used, and then we're introduced to in Algebra 1, even though we're still in calculus. Many years later, still using the same stuff that we learned before. We have the idea that you need a point and a slope to find the equation of a line. So we have y minus 0 is equal to this what's called instantaneous rate of change of the parabola, because it's always changing. It goes from increasing really fast to increasing kind of slow to not increasing at all to decreasing, negative slopes. When x is 0, that instantaneous rate of change is 3. And we have y is equal to 3x. Yeah, we had an x-intercept, or excuse me, a y-intercept of 0, and if you go up 1, 2, and 3, I should be hitting the line, and indeed I am. So we have a graph with the original parabola opening down, a graph laid on top of it, a representation of the derivative function, and a representation of the tangent function, giving us that instantaneous rate of change at x equals 0. Now I regret that I erased all of that, because all you have to do, you have that definition of a derivative where you had the x's showing up. If you just replace that with f prime of c, and everywhere in your work, just write that c value, that x equals 0 value, you can get that same answer of 3 with a tiny bit of simplified algebra, but it's not that less complicated. And you just get a numerical answer of 3 when x is 0. If you want to find the slope then at some other number, say x equals 4, you have to go through that whole limit process again to find a new answer. Whereas if you have the derivative function, you just plug in 4, or any number for that matter, that you would, where you would like to find the slope. Now, that is the definition of a derivative worked out for you one time as an example. Now, there's another alternative form of the derivative, and it's honestly a better, if you will, form for finding the slope of a curve at a point. It's still going through the limit process, so it's still a little bit arduous, a little bit longer than what you'll be learning here in the next section. But it says that f prime of c is equal to the limit as x approaches c of f of x minus f of c over x minus c. Now there's no way to really use this alternative form for the definition of a derivative at a point. You're not going to be able to use this process to find a derivative function, but it is a quicker technique for finding one individual, finite slope at a point. So we have f prime of 0. We're going to still find, again, the slope of this parabola at 0, 0. F prime of 0. Notice I am only using the, well, you might not notice because the x and y values are the same, but we're only using the horizontal position along the x-axis to calculate slope. F prime of 0 is equal to the limit as x approaches c of f of x. Let's actually put the equation in there, or the function in there. So there's a lot less writing there, and all I have to do really is to calculate what f of 0 is. I'm going to erase this and put it in because we can see from the picture, or we can see by putting, where are we at? F of 0 is equal to 3 times 0 minus 0. Well, that's going to be 0. Well, what happens? Of course, adding and subtracting by 0 doesn't do anything. It's the additive identity. So our numerator has two terms in it, both with a common factor of x. And we have that variable of x in the denominator, which isn't always necessarily a problem. C is equal to 0. But we need to be able to plug that c value of 0 in here, and I don't want to divide by 0. We can't, in this format right now, we are in the form of 0 over 0, a form of indeterminate. The limit may exist and it may not exist. The two-sided limit may exist and may not exist. So we're looking at the limit as x approaches 0 of, we're going to take out a factor, common factor of x in our numerator. So we have x times 3 minus x over x. That's going to allow us to cancel out these common factors, and anything divided by itself is 1. And the limit, as I'm starting to want to write delta x, but that's not in the alternative form for the definition of a derivative at a point. The limit as x approaches, not at, but approaches 0, of 3 minus x is 3 minus 0, or 3. So we have that same instantaneous rate of change for the parabola when x equals 0 of 3. That's it. Now, if you're in pre-calculus in chapter 11, this actually may not be at the end of a pre-calculus book, this alternative form for the definition of a derivative at a point, but if you're in pre-calculus being introduced to the idea of derivatives, you might start to think that you can take a derivative and find a slope of a curve just anywhere. But if a curve goes vertical, if the curve has a sharp bend, or say the end point of a closed interval, the end point of a closed interval, not the end point of an open interval, but the end point of a closed interval, those are locations where you cannot identify slope. And it's very common on the AP test that they work with you on maybe giving you a problem, a free response question that's asking you to justify why a derivative does not exist at a sharp bend. And we're going to visit this in our next lesson. But to really be able to understand and explain in a calculus type process why there is not a derivative at a sharp bend, the only way you can truly do that is with the understanding, now, okay, this is the alternative form, but this is a two-sided limit. And to validate why there's not a derivative at a sharp bend requires you to analyze the left-hand limit and the right-hand limit separately, show that they're not equal, thus justifying that the two-sided limit does not exist. So you have to justify that there's no derivative, or you can't find derivative at a sharp bend, by displaying the fact that you understand that the definition of a derivative, or derivatives, really do come from a two-sided limit. And we're going to start learning all kinds of different ways of taking derivatives, arguably shortcuts, if you will. I don't like to call them that because they can get pretty complicated still, but we don't want to forget that derivatives really are the result of a two-sided limit, not just some arbitrary formula. So I'm Mr. True. Bam! Go to your homework.